In this lesson, we're going to learn how to solve exponential equations using logarithms. Now, I want you to notice that in the previous lessons, we solved exponential equations where we were able to get the bases to be like bases, and then we were able to use the idea of one-to-one properties of logarithms. So remember in a previous lesson, if you look at the base 8 and the base 16, I can write 8 as 2 to the third power, and I can write 16 as 2 to the fourth power. And so in this case, I can solve this exponential equation by getting the bases to be equal. So in place of 8, I'm going to substitute 2 to the third. And so I get 2 to the third, and that's raised to the x plus fifth power, equal, and 16 is 2 to the fourth, and that's being raised to the 2x power. And so remember in a previous lesson, you also remember when you multiply like bases, when you have a power raised to power, you multiply those powers. And so this becomes 2 to the 3 times x plus 5. So notice parentheses are needed here because both of those terms are being multiplied by 3. And over here, I have 2, and then that's 4 times 2x. And so we know that if I have two exponential expressions equal to each other and the bases are the same by the one-to-one property, then that means that those exponents have to be equal to each other. So I get 3 times x plus 5. So that exponent must equal this exponent. And so notice I have this linear equation. So let's go ahead and get rid of the parentheses. So I get 3 times x is 3x, and then 3 times 5 is 15, equal, and then 4 times 2x is 8x. And so solving this linear equation, I'm going to just go ahead and subtract 3x from both sides. And when I do that and combine like terms, 3x and a negative 3x is 0. So I get 15 equal, and then 8x minus 3x is 5x, and then dividing both sides by 5 and reducing, I get x to equal 3. And so that's your solution. So when x is 3, then the left side is going to equal the right side. And so in the previous lesson, that's how you solve a exponential equation where you are able to get the bases to be equal. In this lesson, though, you notice that this base is 4 and this is 27. There's no way that you can write 4 and 27 to get the same base. So we have to do a different approach. We have to try something different. And that approach is to use logarithms. And so one of our properties that you learned in a previous lesson is the one-to-one property. And so that property said this. I'm going to use this from here. If m equals n, then I can take the log of both sides with some base b. It does not matter what the base is. Does not matter what the base is as long as it's a proper base, meaning that the base has to be positive and it cannot equal 1. Okay? All right, so what this one-to-one property then says is this. If I want to solve for the variable x, which is located in the exponent, then I have to get that expression, that algebraic expression that has that variable x, out of the exponent. The only way to do that is to take the log of both sides. So I have the log of 4 to the 2x minus 5 equals the log of 27. Now, just some reminders. Remember, you don't see a base there, right? Well, remember that base is understood to be 10. And that's a good thing because at some point you're going to approximate the solution and you'll be able to use your calculator. See the log function right here. Recall, the log function right here that I'm pointing to has base 10. The natural log has base e. Just another reminder, I took the log of the log of both sides, right? Someone else could have taken the natural log of both sides. It does not matter. does not matter. Because remember that one-to-one property, that I'm going to write it here, that one-to-one property says this, that if m equals n, then I can take the log of both sides, regardless of what the base is. But since I'm using a calculator, then I would like this base to be 10 or e, because my calculator can evaluate those functions for base 10 or e very easily. There's a specified button for it. Okay? All right. So it did not matter which one you use. I'm going to go ahead and stick with the base 10 with a common logarithm. So this is natural logarithm. This is the common logarithm, base 10. All right. Now, I can now use the power rule. So remember the power rule. The power rule says this. And let me go ahead and write it so you can see it. The power rule says this, that if I have the log of m to some power p with base b, then I can rewrite this. I can rewrite this expression by taking that exponent, that power p, and writing it as a product. So this becomes p times the log of m base b. So that's a power rule. So that means this. That means then I can take this exponent here and I can write it as a product. And so this becomes 2x minus 5. Now, I'm going to tell you what some students will do. They'll do this, 2x minus 5 times the log of 4. Mathematically, that's not correct. The log of 4 has to be multiplied by both of those terms that's in the exponent. So you need parentheses. Parentheses are important. And then that's going to equal the log of 27. Now, remember, we got to solve for x. So first of all, I got to get rid of those parentheses. So I'm going to use a distributive property. Now, just a reminder, the log of 4 is a real number. All right, so it's a real number. It's a number. You can actually figure it out. You can actually figure out what the log of 4 is. So log 4, press equal, and there's your real number. Now, it doesn't terminate, right? So that's an irrational number, but it's still a real number. All right. Okay, now, so now when I distribute, I get 2x times the log of 4, just like this, minus 5 times the log of 4 equals the log of 27, just like that. Okay? Now, remember, I got to solve for x. So there are 3 terms that I see. 1, 2, 3. This is the only term that has the variable x that I need to get by itself. So I'm going to go ahead and get rid of this term. So since I'm subtracting 5 times the log of 4, I'm going to go ahead and add 5 times the log of 4 to both sides. All right, now combining like terms on the left side, these are like terms right here. Those are like terms because the arguments are the same and the bases are the same. So those are like terms. A negative 5 log 4 and a positive 5 log 4 is 0. So I get 2 times x times the log of 4 equal. Now be careful, these are not like terms. For even though the bases are the same, the arguments are different. So those are not like terms. So all you can do is write it as the log of 27 plus 5 times the log of 4. And then I got to get x by itself, right? I got to get x by itself. Now notice that this is all product right here. These are all factors. So remember, multiplication is commutative. The order in which you multiply does not matter. So I just want to show you something. And you don't have to do this, but I want you to realize that I can rewrite this as 2 times the log of 4 times x, right? And that's going to equal the log of 27 plus 5 times the log of 4. And then to get x by itself, right now multiplying by this real number, this coefficient, so the coefficient of x is 2 log 4. So the opposite of multiplication is division. So I'm going to divide both sides by 2 log of 4, 2 times the log of 4. And then reducing, so these divide out, those common factors divide out, you get 1. 1 times x is x, equal the log of 27 plus 5 times the log of 4 divided by 2 log 4. Okay? All right, now there's your exact answer. So that's the exact answer right here. So this is exact. Usually, though, they're going to ask you to approximate this. So that's where you need to be able to use your calculator. So let's go ahead and approximate this. And we're going to approximate all of these to 3 decimal places. So 3 decimal places. So the thousandths place. All right, so let's go ahead and do that. All right, so let's do the calculator. Now, when using a calculator, whenever you have two terms like this, it's where you have a term plus another term or a term minus another term, whatever it may be, whenever you have two terms, whether it's in the numerator or the denominator, you need to put that in parentheses when putting this in your calculator. So when using a calculator, I know that whenever there are two or more terms, I need to put the numerator in parentheses or the denominator, whatever. If those two terms are in the numerator or the denominator, I know that they have to be in parentheses. If I don't, then I'm gonna get even though this is the exact answer you did and you did all that work correct, you will, when you enter into your calculator, if you don't put that in parentheses, you're gonna get a wrong answer. All right, so that's the numerator. Now the denominator, you got to think about this. Now notice that this is just one term, but I want you to think about this. It's a product of 2 and the log of 4. Since it's a product of two factors here, put that in parentheses. If you don't, and you're not careful how you're reading this, how you're putting this in your calculator, you're going to get a wrong answer also. Okay? So to be on the safe side, what some students do when they're not really sure whether they need parentheses or not, they put parentheses in both. Okay? So put parentheses in both. Parentheses in the numerator, parentheses in the denominator when approximating these. All right, so here's how you do this. Very simple. Okay, parentheses right here. All right, now you're going to say the log. Now remember, when pressing the log, it automatically puts a parentheses, an open parentheses for that argument. Well, my argument here is 27, right? So you can say 27, close the parentheses for that argument. Then we're at plus, and then 5 log. Again, it opens a parentheses for the argument. The argument is 4, but you got to close that argument, but then don't forget about that outer parentheses. All right. Divide, and then parentheses, 2 log, and then remember, open parentheses for that argument, put the argument in, close it, and don't forget that outer parentheses. And then press equal, and this is your decimal approximation. Now notice though, remember your calculator can only list so many digits. It doesn't stop there. It continues on. It's an irrational number, so it has an infinite number of digits. But we want to approximate to 3 decimal places, the thousandths place, which is here at that 8 right here that I'm pointing to. But remember, you got to look at the next place value. If this is 5 or bigger, which it is, we got to add 1 to this 8. So this becomes approximately equal to 3.689. Okay? Now, so there's your exact answer. There's your approximation. Remember, to be on the safe side, whenever using your calculator, put both numerator and denominator in parentheses just to be on the safe side. Okay? You're definitely going to need it with 2 terms when it looks like the numerator. When you have a factor like this in the denominator, you need it as well. Otherwise, if you're not careful how you're reading this, you could get a wrong answer. Now let's check this. Let me show you how to check this. Even though this is an approximation, and we went to the thousandths place, then the more digits you have, the better you're able to see if this is the solution to your original equation. So let's check this approximation in the original equation to see if the left side is equal to the right side. All right, so we're going to check, and I'm not going to check all of these, but I'm going to check this one. So we have 4 to the 2x minus 5 equal 27. That was the original problem. All right, so where we see the variable x, I'm going to use this approximation. Now, use as many digits as possible. So if you round off to 3.7, then this may not be as accurate as possible. So the more digits you have, the better your check becomes. But we did round off here, so let's go ahead and use what I asked you to round off to. So I asked you to round off to 3 decimal places. So I get 4 raised to the 2 times, that's multiplication, 3.689, subtract 5, and I want to see that's going to equal to 27. Now, when you're going to put the left-hand side in the calculator, but remember your numerator is a product, and you're also subtracting 5. So put that in parentheses, just like this. That's your calculator. So your calculator, you're going to say this now. You're going to say 4 raised, parentheses, 2 times 3.689, subtract 5, close parentheses, and press equal. And notice you get 27.02 and so on. So it's pretty close to what it's supposed to be, right? And the reason it's not exactly 27 is because we approximated. And the more digits you would have, the more digits you have here, the better this gets closer and closer to 27. All right. So based on this, then I am certain that this is correct and we approximated correctly. Okay. All right. So that was number 1. Let's look at number 2. So number 2, again, there's no way I can get those bases to be the same. So I'm going to take the log of both sides using the one-to-one property of logarithms. And so I'm going to take the log of both sides. I'm going to say the log of 6 to the x plus 2 equals the log of 8 to the x power. So remember, the whole idea is to solve for x. Well, x, the expression that contains x is an exponent. So I have to get that exponent out of, or I have to get that variable expression, rather, out of the exponent. And the way to do that is to use the power rule. Okay, now once I take the log of both sides, then I can use a power rule, because it's a power rule for logarithms. It's a property of logarithms. According to the power rule, whenever you have the log, I wrote it out here, whenever you have the log of m to some power p, I can now rewrite this, as long as this is a log right here, I can rewrite this as p times the log of m with that base b. Okay, so notice though that both of those exponents contain the variable. So I'm going to use a power rule twice, right? Use a power rule twice. So this becomes x plus 2 in parentheses. Notice I put parentheses, that's important, equal, and then x times the log of 8. Notice I didn't put parentheses here because that was a monomial. This is a binomial right here. This is more than one term. So now each of those terms has to be multiplied by the log of 6. So I get x times the log of 6 plus 2 times the log of 6 equal x times the log of 8. All right, now I want you to notice that I have 3 terms, 1, 2, 3. These 2 both contain the variable x that I want to solve for. So I've got to bring all the terms that have the variable on one side, everything else to the other side. Now, notice that this term does not have the variable x, that I need to solve for, but this one does. So I'm going to bring everything to the left, to the right-hand side. So I'm going to subtract x from both, x log 6 from both sides, just like this. Okay? All right. Now, combining like terms, these terms are alike because the bases are the same. They're both 10s and the arguments are the same. So x log 6 minus itself is 0. And so 0 plus 2 log 6 is 2 log 6 equal, now remember these are not like terms. Even though the bases are the same, the arguments are different. So you're going to have to write it as x log of 8 minus x log of 6. Now to solve for x, remember one of the properties of that you learned in a previous course and also at times in this course was that you can notice that these 2 terms have a factor of x. I can factor out an x. So we can go ahead and factor out an x here. So you get 2 log 6 equals x times the log of 8 minus the log of 6. And now the coefficient of x is this real number. It's 2 terms. do not make the mistake and say the log of 8 minus the log of 6 is the log of 2. That's not true. Okay? That is not true. So be careful. And if you think that, if you ever think something like that, always verify. You have access to a calculator. So the log of 8 minus the log of 6. So on your calculator, if you do that, watch. The log of 8, don't forget to close that parentheses for the argument, minus the log of 6, close, you get this. So that's approximately equal to 0.125, right? The log of 2, if you look at it, the log of 2 is 0.301. Those are not the same, so don't make that mistake. Those are not equal. All right, so be careful. All right, so all you can do now is to get x by itself is notice that I'm multiplying x by this real number right here, these two terms. So to the opposite of multiplication is division. So let me go ahead and rewrite this over. And so I'm going to go ahead now and divide both sides by this coefficient, log of 8 minus the log of 6. Okay, both sides, log of 8 minus the log of 6. And then reducing, these two factors reduce. So I get factor 1 times x is x, so I get x equal 2 log 6 divided by log of 8 minus the log of 6. All right, so there's your exact answer. Now let's go ahead and approximate this. So just like we talked about, whenever you have two terms, you definitely need a parentheses. So when using your calculator, you are going to have to put that in parentheses. Now notice the numerator this time is the one that has that product, right? Whereas in the previous one, it was the denominator. And so when that product, that monomial that has that product here occurs in the denominator, you need the parentheses. The numerator you don't. But remember, as I said, many of you are not comfortable knowing when do you need the parentheses, when do you don't. What I would do is I would use it always, just to be on the safe side. So 2 log 6 divided by log 8 minus log 6. Okay? So let's go to approximate this using our calculator. So we have parentheses 2 log, now notice that it puts an argument there for you. I mean parentheses with that argument. Don't forget to close that argument, but don't forget you have that outer parentheses here that you have to remember to put. Divide by parentheses log 8. Don't forget to close that argument. Subtract log 6. Don't forget to close that argument. And don't forget that outer parentheses, okay? And then press equal. And so this is approximately equal to 12 point, remember 3 decimal places, 1,000ths place. So we got to round off here. So I need to look at that next place value. Since that's 5 or greater, the 6 becomes 7. So 12.457. Okay? All right, now let's check this one to verify that this is correct. So our original problem, always go back to the original. So 6 raised to the x plus 2 power equals 8 to the x. So I receive the variable x, I'm going to substitute 12.457. Now the more digits you have, now remember this is where I wanted to round off, but the more digits you have when you're checking, the better you're able to verify that the left side is going to equal the right side using that number. So 6 raised to the 12, remember x is 12.457, that approximation, plus 2. And I want to see if that's going to equal 8 raised to the x power, which is approximated to be 12.457. And one of the things that this helps by checking is to make sure that you did all this correct. Because if this is incorrect, then these two will not be equal to each other. So then you realize, hey, those are not equal. I did something wrong. So I need to go back and see what I did incorrectly. All right, now remember, these are two terms. You got to put that in parentheses when using a calculator. So we have 6 raised to the 12.457 plus 2, close, equal, oops, I got a syntax error, so let's do this again. All right, so let's do this again. So 6 raised, parentheses, 12.457 plus 2, close the parentheses, equal. All right, now notice, I just want you to verify, see this is in scientific notation, okay? It's because that's a huge number. You can see that it's huge. 6 raised to the 12 plus 2 is 14, so it's approximately equal to 14, that numerator. So 6 raised to the 14th power is a very big number. So your calculator has to put this in scientific notation. So let's go ahead and do that. So this is going to be about 1.8 times 10 to the 11th power. Okay? Over here, hopefully this is about this as well. So 8 raised to the 12 point. Now notice I don't need parentheses here because that's just one number. This was a sum here. 12.457 equal, and notice I get the same thing. So 1.8 times 10 to the 11th. Okay? All right, so what I did was correct here. But that's checking helps you to determine if you did this correctly. Okay? All right, that was number 2. Let's look at number 3. So number 3, we have this. Now, I put this as number 3 for this reason. I want you to notice that when we did number 1, we said that we could take the log of both sides, that common logarithm, or we could take the natural logarithm of both sides, right? Well, whenever the base is 10, you should, to make things so much easier on yourself, you should take the common logarithm of both sides. Now, you can take the natural log of both sides, but it's going to be a little bit more work. You'll get the same answer. It won't look the same, but it'll be the same answer. But it's so much easier since this base is 10, that you take the common logarithm of both sides. And I'll show you why. Oops, I'm sorry, that's 7 to the x, excuse me, log of 7 to the x. Okay, so using the power rule now, I can take these exponents, the variable expressions out of the exponent in both cases. So I get 5x minus 2 times the log of 10, right, equals x times the log of 7. Now remember the log of 10, so that's one of the things you learned about in the previous lesson. What is the log of 10? That's something you have to know right away. Well, I'm hoping, if you think about it, that the log of 10 is equal to 1, right? Because the base is 10 right here. So 10 to what power equals the argument, which is 10? Well, 10 to the first is equal to 10. So you have to recognize that the log of 10 is 1. That's one of the lessons you've learned last week or a previous lesson. So this right here becomes 1. So I get 5x minus 2 times 1, right? Times 1 is equal to x log of 7. But I want you to realize that 5x minus 2 times 1 is just 5x minus 2. And that's equal to x log of 7. Okay, now, notice I have 3 terms. 1, 2, 3. These 2 terms here have that variable x. So I've got to bring all the terms that have the variable x to one side. Since this is the only term without the variable x, I'm going to go ahead and subtract 5x from both sides. It does not matter whether you bring the variables to one side or the variables to the other. It does not matter. Just like with linear equations that you dealt with before. It did not matter. Okay, so subtracting, combining like terms, 5x minus 5x is 0. So you had negative 2 equals x log of 7 minus 5x. Now, just to, and you may not recognize this, but I'm hoping you see this, that this equation right here that I'm pointing to, that is actually a linear equation. Your variables both have, your exponents both have both have the number 1. So x to the first, x to the first. Now, even though you say, well, that's a log 7, but remember, log 7 is a real number. It's a real number. So this is linear. All right, now it's not. Now you cannot combine that because this is a log 7, so that's an irrational number. This is a negative 5 is a rational number. So the best thing to do here is to go ahead and factor out an x. So I get x times the log of 7 minus 5 equals -2. And then just like we did in another problem, this is my coefficient. And again, don't say the log of 7 minus 5 is the log of 2. Okay, so mathematically that's not correct. All right, so note, just to verify, just to make sure you understand this, is not equal to the log of 2. Okay, so be careful. All right, so I'm going to go ahead, and let me go ahead and just rewrite this over. So I'm going to go ahead and divide both sides by the log of 7 minus 5 in both cases. Log of 7 minus 5. And then let's go ahead and notice that these two factors here divide out. You get 1. X times 1 is x. And there is your exact answer. -2 divided by the log of 7 minus 5. Okay, now we're going to approximate this. So remember in your calculator. So in your calculator. Now notice that -2 is just one factor, right? So you really don't need parentheses, but as I mentioned, if you feel comfortable doing that because you're not sure, then put that in parentheses. And then the parentheses in the denominator, log 7 minus 5. All right, so using the calculator, here's what we get. Okay, so -2, put parentheses. Parentheses, -2, close the parentheses, divide by parentheses log 7. Remember that argument, you got to close it right away. And then minus, subtract 5. Don't forget to close that outer parentheses, and like I did now, and then press equal. And this is approximately equal to 0.481. So the thousands place, this is a 1. You have to look at the next digit. Since that is less than 5, the 1 stays 1. And that's it. So that is number 3. Now, remember, when we start talking about number 3, we said that since the base is 10, it's easier to use the common logarithm. I want to do this again. I want to do number 3 again, just to show you something. Okay. All right. I want to do number 3 again, just to explain this. So since the base is 10, it's easier to take the common log of both sides. But someone else could have done the natural log, although most people will not. But it's still okay. It does not matter what the base is. But since I'm using a calculator, make sure you either use the natural log right here or the common log. I'm going to use a power rule now. So I'm going to take that expression, put out in front, using the power rule. So I get 5x minus 2 times the natural log of 10 equals x times the natural log of 7. Now be careful, the natural log of 10 is not 1. Okay? You can see that. You can even see that's not true. Natural log of 10 is not 1. Okay? So that's why we indicated that since this is 10, use common logarithm because the log of 10 is 1. And then that simplifies this into that very nice linear expression, 5x minus 2. But here, that's not nice anymore because now you have to distribute this. And so we get 5x times the natural log of 10 minus 2 times the natural log of 10 equals x times the natural log of 7. See that? So now you see every term has a log in it, whereas this one, it was only this one term. Okay, now let's go ahead and bring all the variables, the variable terms to one side. So it's easier just to bring this one over. So I'm going to go ahead and subtract 5x times the natural log of 10 from both sides, and combine like terms. 5x natural log of 10 minus 5x natural log of 10 is 0. So I get 0, and a -2 natural log of 10 is a -2 natural log of 10 equal, and then this becomes x natural log of 7 minus 5x natural log of 10. Remember, we got to solve for x, so now I'm going to use I'm going to factor out the x here. That's my common factor. So I get -2 natural log of 10 equal x times natural log of 7 minus 5 natural log of 10. And they get x by itself. I'll multiply them by this real number right here. So the opposite is to divide both sides by that coefficient, just like this. And let me go ahead and do that. Divide both sides by that. And then these divide out. And so I get x to equal -2 natural log of 10 divided by the natural log of 7 minus 5 natural log of 10. That is the answer as well. So notice that this and this don't look the same, right? They look totally different. That's because in one expression I use natural logarithm, and in the other one I use common logarithm. But they are the same answer. You just don't, they don't look the same, but they are. So remember how we got this approximation right here to be 0.481? Watch what happens here. So let's use a calculator. So you get -2 natural log of 10 in parentheses divided by parentheses natural log of 7 minus 5 natural log of 10. Put that in parentheses. Numerator, denominator. All right, so let's go ahead and do that. Parentheses -2 natural log of 10. Close that parentheses, but now we got to close that outer parentheses here. Divide by parentheses natural log of 7. Close that argument, minus 5, natural log of 10, close that argument, but don't forget you have that outer parenthesis, so close it, press equal, and you see you get the same thing, 0.481, okay? All right, so it does not matter whether you take the log of both sides, common log of both sides, or the natural log of both sides. But since the base was 10, it makes life so much easier for you if you take the common logarithm, because then you could use this property right here. The log of 10 is equal to 1. Okay, let's look at number 4. All right, number 4, we have this. Now notice this is base e. So since it's base e, let's use natural log, right? Let's use a natural logarithm. So I'm going to take the natural log of both sides, just like this, because remember the natural logarithm is understood to have base e. And so the natural log of 8 to the x plus 2. So now I can use the power rule. So I'm going to go ahead and take both of those expressions and write as a product. And so this becomes x plus 6 times the natural log of e equals x plus 2 times the natural log of 8. Now here's something I want you to remember about the natural log of e. So remember the natural log of e, if you think about the natural logarithm, that natural logarithm here means the same thing as log base e. So I'm taking the log base e of e, and just like this one, just like this right here, the log of 10, to see how when the argument and the base are the same, so whenever the argument and the base are the same, then that expression simplifies to the number 1. So see how the base here and the argument are the same, then that expression should equal 1. And it does, because look, if you change this log equation to an exponential, you're asking yourself e to what power equals the argument. Well, the base is the same, so the exponents have to be equal. So that box must equal 1. All right, so this is 1 right here. And so x plus 6 times 1 is x plus 6 equal, and let's go ahead and distribute this. I get x times the natural log of 8 plus 2 natural log of 8. All right, so every term, there are 4 terms here, 1, 2, 3, 4. Every term that has a variable x, I'm going to go ahead and bring to one side. So let's go ahead and bring them to the left side. So I get x minus x natural log of 8 equals, and then we'll bring the 6 to the other side. So I get 2 natural log of 8 minus 6. All right, so I brought x natural log of 8 to the left and then 6 to the right. All right, and then factoring out the x here, I get x times 1. X times 1 is x, right? Minus, and then x times natural log of 8 is x natural log of 8. Equals 2 natural log of 8, that's the natural log here, minus 6. And then to get x by itself, we're going to go ahead and divide both sides by this coefficient. So I'm going to divide both sides by 1 minus natural log of 8, just like this. And these divide out. These are common factors, so those divide out. X times 1 is x equal 2 natural log of 8 minus 6 divided by 1 minus natural log of 8. And so there's your exact answer. And so if we approximate this using the calculator. And so on your calculator, you're going to put the parentheses, the numerator in parentheses, and you're going to put the denominator in parentheses also. All right, so let's go ahead and do that on the calculator. So you have parentheses 2 natural log of 8. Notice that put a parentheses there, so you got to close that argument. Subtract 6. Don't forget that outer parentheses. Divide by parentheses 1, and then minus the natural log right here of, now notice that, remember, put the parentheses here, right? So you got to close that parentheses. Put 8 there, close it, and now you need to close that outer parentheses right here. Press equal, and that is approximately equal to, remember, 3 decimal places, so the thousandths place. So the 5 is in the thousandths place, so I got to look at the next digit. Since that is greater than 5, greater than equal to 5, this 5 becomes 6. So 1.706. All right? Okay. Now let's go ahead and check this. And I just want to show you how to check this. So let's check this. Check x is approximately equal to 1.706. All right, so we have e, the original problem, e to the x plus 6 equal 8 to the x plus 2. So wherever I see the variable x, I'm going to substitute 1.706, right? So I get e to the, remember when using a calculator, you got to put the exponent in parentheses since I have two terms here. 1.706 plus 6, and we'll see that's going to equal 8 to the, in parentheses, 1.706 plus 2. Okay, so let's check this one. Now, this is going to be a big number, so let's see if we'll put in scientific notation. So I get, remember, this is e, so remember how to get e. Make sure you remember how to do that. To get e, you're going to press second ln. See that? Remember that? Okay, 1.706 plus 6, close the parentheses, equal. All right, so that is about 2221.64, right? Okay, and over here, I get 8 raised to the parentheses 1.706 plus 2, close the parentheses, press equal, and you get the, oops, it's a little, well, so it's a little off because remember we rounded off here. So notice it's almost close. It's 2222.55, right? So it's a little off because of the rounding. So if I went ahead and maybe put a couple more digits, then this would get closer and closer together. So just be aware, depending on how you round off, sometimes it's a good rounded to 3 decimal places, sometimes good enough to verify those are equal, and sometimes it may be a little off. This one is off by about a one's place or so. Okay? All right, so that was number 4. All right, number 5. And that should be the last one, I think. All right, so that would be number 5, the last one. So notice that the base here is 9, the base here is 15. There's no way I can get those bases to be the same. So I'm going to go ahead and take the log of both sides because my variable occurs in the exponent, actually on both sides. So let's go ahead and take the log of both sides to get the log of 9 to the x plus 4 equal the log of 15 to the x minus 1. And now I'm going to use the power rule. All right, so the power rule. So the power rule allows me to take that exponent and write as a product. So the first thing you have to do, though, is make sure you took the log of both sides. So you have to have a logarithm here to be able to use the power rule. All right, so I get x plus 4 times the log of 9 equal x minus 1 times the log of 15. Notice you have to put those in parentheses because the log of 9 has to be multiplied by both of those terms. The log of 15 has to be multiplied by both of those terms. All right, and then distributing in both cases, I get x times the log of 9 plus 4, that's a 9 here, plus 4 times the log of 9 equal, and over here I get x times the log of 15 minus the log of 15. Okay, now again I have 4 terms, 1, 2, 3, 4. These 2 right here, those 2 are the terms that have the variable x. So let's bring those to one side and everything else to the other. So I get x log 9 minus x log 15, right? Equal, and then when I bring this over, that becomes a negative 4 log 9, negative 4 log 9 minus log 15. All right, now factor out an x here. I get x times the log of 9 minus the log of 15 equal negative 4 log 9 minus the log of 15. And then you get x by itself. We're almost done. Get x by itself. Since I'm multiplying x by this real number, I'm going to go ahead and divide both sides by that coefficient, by that real number. Just like this. Log of 9 minus the log of 15. And so these divide out. And so I get x is equal to negative 4 log 9 minus the log of 15 divided by log 9 minus the log of 15. Now be careful. I don't want you to think that these right here divide out. So be careful. This numerator is not the same as this denominator because that log 9 here is being multiplied by negative 4. So be careful. Don't say that this divides out. It does not, because this factor that you see down here is not this. Okay? They're totally different. So this is your answer. That's your exact answer. Now let's go ahead and approximate this. So remember, if you're going to approximate in your calculator, put both of those in parentheses. Okay, so in parentheses, the numerator, so negative 4 log of 9, close at 9, subtract log 15, close at 15. Don't forget though, you had an outer parentheses, right? So don't forget to close that. Divide by, and then parentheses in the denominator, log 9, close at 9, subtract log 15, close at 15. Don't forget though, you have that outer parentheses here that you have to use. Okay, that's this right here. And then press equal, and so that's approximately equal to 22.507. So remember, 3 decimal places. So the 6 here is in that I'm pointing to is in the thousandths place. So you got to look at that other digit, which is also a 6. Since that is greater than or equal to 5, the 6 becomes a 7. And so that's it. So that is the lesson on using logarithms to solve exponential equations where the bases could not be the same. Oh, and I want to remind you of this. I just want to show you something. So remember that first problem we did, if I can find it real quick, that first problem we did where we were able to get the bases to be the same. So I'm hoping you understand also that if even though I could get the base to be the same, I could also do the same problem with taking the log of both sides, right? So I just wanted to show that. But always make sure you follow the directions, because the directions may say solve this exponential equation by getting the bases to be the same. So always make sure you're following directions. But I just want to show you that you would still get this answer of 3, by using logarithms. So let's do this real quick. So I'm going to take the log of 8 to the x plus 5 equals the log of 16 to the 2x. And so then using the power rule, I'm going to rewrite these exponents as a product. And so I get x plus 5 times the log of 8 equals 2x times the log of 16. And now distributing, I get x log of 8 plus 5 log of 8 equal 2x log of 16. Okay, now I want you to notice that these two terms here, there are three terms, 1, 2, 3, but the outer terms are the ones with the variable x. So let's go ahead and subtract x log 8 from both sides, just like this, x log 8. And x log 8 minus x log 8 is 0, so I get 5 log of 8 equals 2x log of 16 minus x log of 8. And then factor out an x here, I get 5 log of 8 equals x times 2 log of 16 minus the log of 8, right? Okay, and so now dividing both sides by 2 log of 16 minus the log of 8, just like this, 2 log of 16 minus the log of 8, I get, and remember these divide out, so I get x to equal 5 log of 8 divided by 2 log of 16 minus the log of 8. Okay, now you may say, well, that does not look like 3, right? That does not look like 3. But if you were to use your calculator, notice you will get 3. So you get parentheses 5 log of 8, close and then close, divided by parentheses, the denominator now, 2 log of 16, close that argument, and then subtract log, parentheses, oops, sorry, it already had a parentheses, log of 8, close that argument, and don't forget to close it out of parentheses, and notice I get 3, x equal 3. But whenever, mathematically, whenever you see those bases, you can write those bases with the same base. We want you to do it that way. Don't take the log of both sides, because then you will not really see that this expression really is 3. Now let me show you that. So let's suppose you did not have access to this calculator. And I want to show you how to get this 3, since if you don't have access to the calculator. So you have 5 log of 8 divided by 2 log of 16 minus the log of 8, right? Okay, so here's what you would do. You would say, all right, well, I know that 5 log of 8, using the power rule, I can write as a log of 8 to the 5th power, right? Those two are the same. Divided by, and over here, if you look at 2 log 16, I can write 2 log 16 as a log of 16 squared minus the log of 8. And then you see that denominator, since the bases are the same, I can write this subtraction using the quotient rule. Remember you learned about the quotient rule for logarithms? So that means I can write the numerator as log of 8 to the 5th, but I can write the denominator as a quotient because that's a subtraction, and the bases are the same. So I can write this as log of 16 squared divided by 8. And then the numerator here, I can write as log of 8 to the 5th divided by, now let's think about the denominator. So I want you to think about this for a moment. Okay, look. So the log of 16 squared means 16 times 16, right? Right? Divided by 8. Y'all agree? All right. Now, this 8 divides, 8 divided by 8 is 1, and this 16 divided by 8 is 2. Okay? So this becomes 2 times 16, which is 32. So that becomes a log of 32. So that's going to be my denominator, log of 32. All right. Now, I want you to recognize that the log of 8 to the 5th is being divided by the log of 32. And so I want you to think of this now. Let's go ahead and think about it this way. All right, so this 8 to the 5th, I want you to think about this 8 to the 5th. So 8 to the 5th, that 8 I can write as 2 cubed, right? And so that's 2 cubed raised to the 5th power, which is 2 to the 15th. So my numerator then becomes the log of 2 to the 15th. The denominator, log of 32, well, let's give 32. 32 you agree, is 2 to the 5th power, right? 2 to the 5th power is 32. So it becomes log of 2 to the 5th. And now using the power rule again, this becomes 15 log 2 divided by 5 log 2. And then these log 2's now divide out, and you get 15 divided by 5, which is 3. So that's how you could have done this without having access to a calculator. But just to remind you, whenever you can get those bases to be the same, we want you to do it using the approach you've learned previously, where you do get the bases to be the same. And you don't use logarithms. Just go ahead and do this naturally without using the idea of logarithms. Because when you use logarithms, then you really cannot see very quickly that this is 3. Okay, so that is the lesson on solving exponential equations using logarithms.